let's look at a short-circuited quarter wavelength. So SC short-circuited, lambda over 4, and we're looking at the resonance frequency of this. So this one is actually a parallel type of resonance. It almost looks like an anti-resonance, so the end is going to drift up and down, which is fine. We want that to behave like that on purpose, so this is achieved by using a quarter wavelength short-circuited transmission line. So it's the same pictures that we had before, but the wave fronts will look different, and because it's lambda over 4 instead of lambda over 2. And you can see that by taking a quarter wavelength back from the picture you already looked at. So we're going to look at this from the input impedance, and so we're going to recalculate all of our impedance values, input and otherwise, and verify the equations are going to change by 90 degrees, well, for the most part. So Zn is still the same as it was. Z naught, tangent, hyperbolic tangent of alpha plus j beta times L. Right, so we're not looking at lossless. And this is actually we're going to do some math in here, and we're going to convert this to something a little more useful. Well, it won't look more useful, but it is more useful. So this is hyperbolic tangent of alpha L, right, plus j tangent beta L. And then this is over 1 plus j. Oh, sorry. No. That's series. All right, let's talk about this is a short circuit quarter wavelength. This is tangent. Oh, I did do it right. I was looking at the wrong part. I apologize. 1 plus j tangent beta L hyperbolic tangent alpha L. Okay? This is where it's getting a little confusing because I don't want it to look like this. I want to change this around. And one of the things that your textbook does is to make this a little easier to work with. We are multiplying the top and bottom by minus j cotangent beta L. Okay, so we're going to multiply it by 1, which just happens to be minus j cotangent beta L. We're just changing the form of this to match closer to what we need it to for the rest of this problem. Okay, so this is now 1 minus j hyperbolic tangent times alpha L times the cotangent of beta L. And this is over hyperbolic tangent of alpha L minus j cotangent beta L. Now, the reason we're doing this is we're gonna actually cancel some of this stuff out. We're gonna simplify some of this stuff later on, just like we did the last time. Short chain, not lossless, but minimal loss, that type of stuff. So we're also going to go with L equals lambda over 4, something we previously stated, and this is at omega equals omega naught. Right? So we're going to say that this is true, your resonant frequency at lambda over 4, or anti-resonance for this case. Now we're going to, because of this, we're going to let omega equal omega naught plus some delta omega. So we're going to, again, do the same thing. We're going to see what happens off of omega naught, the resonance frequency. And then for, this is a TEM line. Again, we are going to say beta L is equal to omega naught L over our phase velocity plus this delta omega L over our phase velocity. And then we're going to state that because of other how this works out with beta L, we're going to state that this is pi over 2. So that is the solution for this, plus pi delta omega over 2 omega naught. So we're starting to see some things change based on the quarter wavelength. Okay. We're also going to state that cotangent of beta L is equal to cotangent of, we're going to add this stuff in, pi over 2 plus pi delta omega over omega naught. Okay, and all we're doing is replacing this beta L in here and putting it in there. Well, this has a nice setup for it, because now this is actually equal to, because cotangent of pi over 2 is 0, so then we end up with some other terms in here. We're going to say this is equal to negative tangent of pi times delta omega over 2 omega naught. I'm sorry, there's supposed to be a 2 in there, right? So don't forget the 2. Okay? And then this is approximately equal to negative pi delta omega over omega naught, so 2 omega naught. So, and this is just because there's so small deviation in this that these are essentially the same. Enough that we can do this for the math, for the hand calculations. Then we're going to assume low loss, which therefore my hyperbolic tangent of alpha L is approximately equal to alpha L. Okay, so low loss. No problem. Now our input impedance is therefore Z naught and 1 plus J alpha L times pi times delta omega over 2 omega naught, and then the denominator is just alpha L plus J pi delta omega over 2 omega naught. Okay, not as clean, looks a little messy, but I'm going to say this is approximately equal to alpha L plus J pi delta omega over 2 omega naught and Z naught in the numerator. Okay, so rather than writing Z naught times, I just wrote Z naught in the numerator. It's just easier. Now, since alpha L pi times delta omega over 2 omega naught is much less than 1. Okay, we're going to state that that whole term is much less than 1. The result of this is the same as a parallel RLC circuit we did in the previous lecture. So this is the same as a parallel RLC circuit. Okay, so the mathematical formulation is going to look the same. That's essentially what I'm saying. And that characteristic, or that impedance value, that input impedance value is 1 over R plus 2J delta omega C. So that is the mathematical equation. So if I compare these two, I can pull out my RLC values. RLC values are, here's R, which equals is Z naught over alpha L. Our capacitance value is pi over 4 omega naught Z naught, and our L value is 1 over omega naught squared C. And the last piece of this is unloaded Q. I'm going to erase this up here just so I can write it, and then I will erase everything and do the open circuited transmission line. So our unloaded Q, that's our Q naught value, is omega naught RC, and this is equal to pi over 4 alpha L, and then this is beta over 2 alpha, and this is true since L equals pi over 2 beta at resonance.